So we are starting the recording here. Today, our goal is to get done with hopefully two, maybe one problem, and I'm happy. This one in particular is the craziest, insane problem ever, but I did get it to work. What? Yeah. Just because I didn't want to do it anymore. I ran late and I just was blah blah at the end. This one here is actually not as bad. I got it done very quickly. So I have a question for y'all. Would you like the easier problem, the second problem, first? Oh, that's a yes. Okay. Okay. I also have to say that this problem here is very pretty because it does things that should be happening with Jacobians. The other one's just a mess. So this one here, it actually acts like a normal Jacobian integral, which is so pretty and happy. Um, the only difference is that here we have a small formula for u and v, versus on this one you'll have just numbers, which seems fine, but then it's not. So whatever. Okay, so yeah, let's do this one first. We've got to write small today, write tiny, and we're going to basically start from the beginning on how the concept works. Okay, what we're wanting to do, our goal, and don't write everything down. I'm going to tell you when to not write down. Don't write this down. Our goal is to say double integral of something du dv, and then it's happy times. Okay, that's what we want. That's our goal. Can I integrate this right now? Just looking at it right now, is this something that's easy to integrate? Not at all, and it might even be impossible, depending on how the variables work out. Um, I'm just suspicious. So let's not go down that road. We're instead just going straight Jacobian. So one of the things that we need to do is first off, kind of draw where this is and see what's going on with the region, I guess you can say. We need to convert the region. So this is what we have right now. I have x is equal to y, and x is equal to 4 minus 6y. Just looking right there. And then I have y is equal to 0, and I have y is equal to 4/7. So those are my limits from the integral. It's defining what the region is. We do not need to know what that region looks like. It would be helpful sometimes, and you can certainly use Desmos to kind of help you out. But this is good enough for now. Okay, cool. What we're wanting to do is see where they connect. I want to get intersection points for x's and y's. Okay, so here's an easy one. Why don't I take my y's and I just plug them in individually? Say like this. I got y equals 0. So then what is x equal to here? Yes, 4, but also, and 0, very good. 0 and 4, very good. Because you plug it in here, you get a 0, plug it in here, you get a 4. Excellent, excellent, excellent. Now, let's redo it for 4/7. When I plug it in here, my x would be 4/7. And when I plug it in down here, it's actually 4/7. Isn't that weird? I think. So I want to use some Desmos to verify that one. That's a Desmos scientific right there. Easy math, but still math we need to do. So go bloop. I'm going to say that I have 4 minus 6 times 4/7 is 4/7. Kind of strange, but it works. So you got the same number twice. This should already indicate something kind of strange to you. It's fine, but it says, I wonder what we're actually going to end up looking like here in a minute. Are y'all seeing what I'm seeing so far by plugging them in and getting the intersection points? Yeah? Could I use Desmos to get those? Yeah, much faster. But I want to try, at least on this problem, to not use Desmos graphing. On this problem. The other one, I don't care anymore because it's insane. But yeah, this one we can do this. So I'm going to take each one of my points, my coordinate points, starting with here, 0, 0. And I want to find out what my u and my v are equal to at this point. Now notice we got our formulas up here for that, my u and v. So at 0, 0, what do I get for u and v? Perfect, perfect. Let's go with 4, 0. See, again, I got a 4 for x and a y is 0. What's my u? What's my v? Okay. Cool, cool. Thank you. James, you have competition now.
Oh, no, it's fine because I'm completely lost.
I'm so happy. Thank you. He's always answering everything. I'm so happy. Please. Continue. Good times. It's good times because these other guys, they don't talk at all. I have to like pull it out of them. Yeah, you're smiling about it. Anyways, this one's a little bit more strange. Now, when I plug in a 4/7 and a 4/7 for V, I get what? For V. That's an easy one. Yes. But the Y, though, is like, what? So I got 4/7 plus 6 times. There you go. And you know what's so funny about this is that we're getting a repeating values, right? You see how we're getting zeros, 4s, and then we got a -4 as well. This is a good thing. We need to see repeating numbers at this point, okay? When I go and do this other problem up here, we'll get the repeating numbers for sure. You'll see lots of 2s and 3s or whatever it is, okay? So seeing okay, that was a mistake. Seeing these zeros and the 4s, that's a good sign that we're doing things right. Okay, good. Good so far? Good? Okay. I want to graph this region, not this XY. I need U and V. U and V. The best way is to plot the points. So I got 0, 0. I got 4, 0. And then I've got a -4 down there. So you connect the dots and you get a triangle down here. This is the region that I'm actually going to be integrating. Okay? It's a triangle. It's not a rectangle. If it's a triangle, I have to have like a function in a way. What I'm going to say is that we still have a top and a bottom. I want to do double integral of my Jacobian times all this other stuff, dv du or du dv, doesn't really matter. But I've got to have like a formula in a way. You're not writing that down, are you? There's way too much space. I ain't got room for that. So I should have warned you. Don't write this. It's too big. What I'm saying is that we need to find out what I'm going to put here to make this thing go. Yeah? Now, you help me a little bit here. I have this region here, and I need to have my limits. I basically need to have like a U equals something, and then a V equals something. Top and bottoms. Go ahead. I like that. That's easy. You got it. I love it. So what about V? Remember that this right here is like my bottom, and this is my top.
Sorry, I know I'm talking a lot now.
Yeah, go ahead. There it is. You got it. Perfect. That's right. -U for my bottom, and then the top. Perfect, perfect, perfect. That's the key trick for this one. V equals -U for that line that's going down to that point. Okay, because again, it's a triangle. We have to have a function in a way right there. Now, I'm gonna say sorry ahead of time that my U's look like 4s. We are gonna have some bad problems coming forward, but can't help it. It's gonna be okay. We're gonna make this thing work. So this is my my limits of integration, and yes, you can write this now. J dot dot dot, and then I have to have a du dv or a dv du. Which one would you think is better? Correct. Yes, because we have v with in terms of u. So yes, yes, yes. 0 to 4, and there you go. This is our integral. What we need to do is find the Jacobian. Still, we haven't figured that one out. And then we got to go back and plug things in to find my variable density in a way. But we're getting there. So now off to the Jacobian. And here we go. We are actually going to be scared once again. Okay, so the Jacobian formula is x sub u y sub v minus x of v times y sub u. It's it's a determinant, but that's just the quick way to do it. I need x and y in terms of u and v. What I have right now is u and v in terms of x and y. Good luck. As in, like, I can't do this. I have to do a lot of math with this now. So here we go. I want to get u and or x and y by itself. X and y are equal to u's and v's. Yeah, that's definitely one way. Both equal the same letter, then plug them both in. I'm going to substitute for one and substitute him for the other kind of thing. So yes, very similar. I'm going to move this guy over because he seems really easy. I'm going to say that y is equal to v plus x. And then I can plug that in right here into my u formula. U is equal to x plus 6 times v plus x. Go away. Okay. Distribute. Combine like terms. And, well, we got something. We got something. But what we're wanting is u and v, no, I'm sorry, x and y equal to with u's and v's. We're really close here. Okay. I need to get rid of this x essentially. It's kind of like I need to solve for x in a way here. Give me a second, like, to think about this here. Oh gosh, I did it. I did it wrong. Did you see what I did wrong? What did I do wrong? Yes, what was I thinking? Oh, that's why I'm like so confused. Like, where am I supposed to go with this? Okay. Now we're better. Now we're better. I can get x by itself. Move this over. So that'd be u minus 6v. Divide by the 7. And so I've got x is equal to 1/7 u minus 6/7 v. This is awesome. Okay. Now I got to go back and find my y. So y is equal to v plus all of this stuff. You don't need the parentheses, but this is a 1, which means 7/7. Therefore, I can say that y is equal to 1/7 u plus 1/7 v. Change my color now. I think I want a green now. I'm going to do green. Okay. Are y'all confirming kind of the concepts, the ideas there? So here we go. Now I can finally find my Jacobian. So derivative of x in terms of u. Perfect. And then y in terms of v. X in terms of v. And then y in terms of u. This is good math. Everybody likes this math. That's a 6, not a 7. This is how Jacobians should work. 7/49, we get 1/7. That's a scalar. I mean, sometimes it ends up not being a scalar, but it's a scalar that's very pretty. We're going to use it with our integral here. Oh man, that we are not done with the setup. We are not done with the setup. Yeah, I know. So let's go back to setting this thing up. Yeah, stop stretching. You got more to do, okay? You ain't got time for stretching up. 1/7 times, and then I have to convert everything. Let me first off, this is a negative u. That's a 0. This is a 0, and there's a 4. And now I've got to convert this thing here into u's and v's. This is the part that's this is the nice Jacobian part, okay? I was at first going to plug in for x's and y's, right? Because we got the x and the y, and we start plugging them in, blah, blah, blah. That would take forever. Do you see a pattern? Do you see a pattern? Do you see a pattern? Yep. Exactly. That right there is a U. This right there is a V. Perfect. That is a good Jacobian problem. Okay? That's a good Jacobian problem. We like this. This is a good thing. So here we go. I got now U, E to the V, dV du, as we've previously discussed. And finally, at this point, we're finally going to do calculus. We're actually going to start integrating now. I have a high tendency to put the J Jacobian on the outside. Actually, it should be on the inside just in case it's a variable. But most of the time, it should end up just being a scalar. That's a good Jacobian. It's just a number. So here we go. I'm going to say the 1/7 in the front, and now we can start integrating. It's first in terms of V. So integrating right here in terms of V, what do we get? Yeah, it doesn't change anything, right? I then have to plug in a 0. And then that would be e. Yeah, e to the 0 is a 1. Very good. Minus, when I plug in this, I would get u e to the negative u. Okay. Well, that's happy times. Until now. Now I get to switch my color again. Let's go brown now. Let's go dark brown. This one's easy. This one's easy to integrate. We're happy about this guy. This one right here, this one is integration by parts. And the problem is that U and V have already been taken. So you can't use those. So I'm going to use A and B just to make things more confusing. So we're going to choose an A and then a DA, and then we have a DB, and then we have a B. Do you want to choose or you want me to? Heck yes. Yes, yes, and yes. Definitely that. The other way would make us go down a terrible road. Yes. Yep. It would get worse and worse. Unless I was able to get it the same on both sides and factor it out to get an answer, which who wants to do that? Yeah. I'm looking at you, e to the x cosine of x. Anyways, so yeah, this would be the other guy. And that anything that looks like a 4 is not a 4 unless it's right here. That's a 4. Okay? So I just wrote a 4. Okay. When I integrate this guy, yep. And then negative e, negative u. Very good. So let's go and do some math. The first part's easy. We like that one. Yay. And then I'm going to then say I got UV, so AB, negative, minus integral of VDU, so BDA, I guess. Close, close. We're going to get there. Well, we're all smiling about a 14 in the denominator over there. This negative, when you distribute it, it cancels both of these guys. Yet this one has one. So it's a positive u e to the negative u minus, and then what's my integral of this guy? Another negative? So now that negative now becomes a positive, also e to the negative u. What? Oh. Have I given you too many minus signs? I didn't see that minus. Yeah, we're good. We're good. Oh gosh, it does. Is this why this is a good test question? Yes. Because you'll forget the things like that that will mess the whole problem up. I almost had it without messing up. I almost did. Almost. Never a day that I can't mess it up though. So this is a 4. Nothing else is a 4. That is a 4. All right. 4 squared is 64 over 14. I don't care. So we'll figure that out later. Plugging a 4 in right here, we get 4/7 e to the negative 4. So everything that looks like a u is actually now a 4. Just wanted to tell you that. Plus, and then we plug this in, we get a 1/7 e to the negative 4. 64 over 14 is a very,
It's supposed to be 16.
Yet again, I messed up. Man. Thank you. Yep, that's the correct answer. Man, I am just not having it today. I messed up on a distribute and a multiply. Gosh, what a terrible math teacher I am. Let's just flash the answer. And yeah, you didn't see that. Why do I have a 1?
Isn't there e to the when you plug in 0, it gives you a 1, so you get
Yep, right here, when I plug in a 0, I should get an additional 1/7. Or no, now because it's a minus, it would be a negative 1/7 there. And then that would make this into a 1. That there. 5/7. Okay, we got it. Thank you guys. The Jacobian part I had down. No problem with Jacobian. As soon as we did any other kind of math, I can't do it. So thank y'all for being there for me. I'll be there for your exam. I will. As in after you're done, I'll grade it. Okay. So that was the easy one. This is hilarious. Did you want me to recap? No. We have a video for that now, right?
It's basically just kind of roughly going. The Jacobian is just solving for u and v with the 2 equations we're doing at the top.
Yep. Once you have it all solved there, that's when you start integrating. And this is where I mess up. Right here, this is the part I mess up. Yeah. Okay. Cool. So can I give you a strategy for these problems? I know I already said it last time. I'm going to do it again. It's called Desmos. This now I know that there will be one on your exam, maybe. I don't know, depending on what I feel like at the time. But we can at least check to see if our integral is working. But you have to get it wrong once. I know that's sad, but you know how the randomization is on these things, right? As in, like, not much. And then you can compare it with their answer. And you now know that, yes, my integral setup is correct. I don't have to waste that time, okay? Though that was only a part of the problem. I get it. Okay? So that's good. Another way that you can, again, cheat, I don't mind telling you this kind of thing. At the very beginning, you type in those limits. And so you got x equals y, x equals 4 minus 6y, y equals 0, y equals 4/7. And this, oh, come on. Does it change into a fraction? You don't want to change it in, it is 4/7. Okay, so now, yeah, okay. 4/7, 0, 0, and then this thing right here. So you can see all your points where they're intersecting. So you don't have to do that part. And you just plug them in like you normally would. I'm trying to, like, any kind of little bit. You get me? Okay, good. You're like, why are you doing this to me, Chad?
Well, I was trying to think for a second. I'm like, it's that green line right there pretty much pointless if that doesn't even come really
Yeah.
part of the equation.
Yeah, sometimes. Sometimes they do that. I wonder if like over here is that. Oh, there's your 4-0. Oh, there it is. It is not pointless. There's an intersection right there.
Okay.
So I guess it's this triangle that they're talking about. Now I'm understanding it. Triangle to triangle. Maybe. Okay. Let's do some terrible math now. I want to show you before we do this that I actually did all this work and I skipped a lot of steps. And I actually didn't integrate at all. I just put this into Desmos. So it is tasking. I will be using Desmos for this one. Yeah, what's up? Oh no, for reals? That makes it so much easier. Okay, we'll get when we get there. But how did you see that?
I was just like, well, I wonder if I can factor that. And I saw the u and the v, 4x times x is 4x squared, and 3y times 2y
Mhm.
is 6y squared. I'm like, I wonder if I just factor it out and see what happens.
Okay, so for the folks at home, I know that y'all are here, but just for the folks at home, if you do this one times this one, you get 4. And if you do this one times this one, you get a 6. 4, 6. So far, so good. Then, if you do the other guys, if you do 4 and 2, and then 3 and 1, you get the 11. So that, yeah, in a way, you could factor that to make that. It makes it a lot easier. So this here is not required. We would do something easier here. Correct? For the folks at home? Okay, folks at home. We'll do that in a minute. Good idea. I'm still going to cheat and use some Desmos. Because, like, I wanted to find the intersection points, and you can see that they're not very friendly. So, like, if y'all wanted to go find intersection points for these guys, right, that would take forever. So I think it's easier just to use some Desmos once in a while. And I have that up here. So I already don't see my answers. No. I'm just like joking with you here. So I put these 4 in, and I get these 4 intersection points. And now that made your life at least 5 minutes faster. Is that okay? Okay. So let's go with that. I have these intersection points. Oh, Chad, we're actually going to do it. You're not just going to tell us that you did it. You're going to do it. Right, Chad? So let me graph this thing. We have 2 lines that are going down kind of quickly. And then I have 2 lines that are not going down as quickly.
This was the problem you were working on yesterday.
Uh-huh.
Yeah.
Yeah. And so we're talking about this little rectangle prism thing. So a rectangle makes a rectangle, but we're going to make it not as wonky. But the intersection points, let me write them all up, is 0, 1, 1.2.4, 1.2, negative 0.6, 2.4, negative 1.2. If you're seeing repeating numbers here, you're definitely going to see repeating numbers with the u's and the v's, which is a good thing. Let's use these guys to find u and v for each one of our cases. So what do I have for u? U and v. And
That would be 7.
2. Very good. Yep. For these guys, I would use Desmos Scientific, which I did. You can see what I did here is I had an x and a y, and I could just plug in whatever I want to my formulas. Now, this is not cheating for once. You see how much faster it is? And my guess is this one. Because we should see repeating numbers, with these Jacobian stuff. Yeah. So those are my actual values. And so therefore, when I start to integrate this, and again, J, some other stuff we'll do, du, dv, or whatever, my u's seem to go from, and the v's, perfect. There you go. So this will be a nice integral eventually. Now that I know that it factors and blah, 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 blah. Y'all are so much smarter than me, blah, 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 blah.
I'm still completely lost, Jeff. If it makes you feel any better.
Really?
No, not really, but
Okay. Well, then you're lying to me.
it's all hyperbole, Chad.
Okay. So I still need to find the Jacobian. So we need to have x in terms of u and v, and y in terms of u and v. Ah, don't you love doing this algebra stuff? Let's do this. So v is equal to no, not v, x. So I got x is equal to v minus 2y. And then I can plug that in right there. So u is equal to 4 times this stuff plus 3y. Okay, I want to get y by itself, so I'm going to move the y over and move the u over. I'm actually going to go to the side here. I don't like that setup. I don't like that. Divide by the 5. So I get negative 1/5 u plus 4/5 v. It's actually better for the Jacobian if you set it up like that instead of have it all distributed by or all divided by a 5. It's easier to have them split up because you know we'll take derivatives of those here in a second. Plugging in this now over here. This should have been a u-do. If you hate us, Chad. Negative 3/5, I believe. I want to make sure that y'all are getting the same thing as me. Normally when you don't yell at me, it's a good thing. But then y'all yell at me, and I'm like, oh no, I did something wrong. Yell is a wrong word. Oh, you're trying to get me back now. It's a subjective word. Okay. So I got those. Now I can finally find my Jacobian. Again, that's xuyv minus xvyu. X in terms of u, and y in terms of v. Sweet. Minus, what do I put here? Beautiful. Thank you, thank you. 8/25 minus, if you look at the end there, so I got 5/25 is 1/5. Very nice. It's nice when we get some easy numbers once in a while. So let's do our integral here, I guess. So I got a 1/5 times, and then you're all going to help me with this stuff. Du dv. Okay, I'm going to pause there. Whew. How many questions are on your homework for this one? 6. How nice of me. I meant only 6. It's not that bad. So y'all were saying that this will factor. So is it both positives or are they squares? U times V. Like, oh, I see, because those are the factors. Like this. Oh. Okay. Cool. That's way easier. So integration in terms of U. Sweet. From 3 to 6. Plugging those in. We get 36 minus 9. Say it again. Oh, I thought you already got it. Was it 25? Oh, no. 27? Yeah, 27. You're right. I'm not going to ask. I already know you got the right answer here. V squared over 2. Oh. Yeah, when you integrate, you don't need an integral sign anymore. Go figure. Plugging that in, I think we just double it, so it would be 27 over 5, which is, flash the answer. It is the answer. Man, that was so much easier. Gosh, I thought this was the hard one. But y'all spotted it. Y'all are smarter than me. I might look smart. It's just because I'm using my full capacity. Okay, but y'all have a higher potential than me. Isn't that how it works? No? Okay.
To be fair, there's been times where I say something that makes someone come out of nowhere and say something even smarter, or me or someone else. So
That guy is pretty smart over there. Huh? Okay. Wow. We got done with the 2 Jacobian problems with a little bit of Desmos once in a while. That was not too bad. And look, we got time. And we can't leave early. Well, I need to go get pizzas soon, so I will leave a tiny early, but not very early. Any questions on Jacobians? Okay, we briefly looked at all the homeworks last time. They do look very similar or easier, so that's a good sign for y'all. If you find something uber hard, you tell me. I just delete it. So, all right. So I know that, oh no, I haven't finished chapter 15, and I know there's an exam between them, but unless y'all have a homework problem, I don't mind. We can do a homework problem. Otherwise, we got to keep going. Was it easy? Okay. So at the start of every chapter, as you know, these are very simple at start, and they are. This chapter 16 stuff will get increasingly harder, but I don't think exponentially harder. I just think that it's so out there that you just try to get as many points as you can before the end of the class. So yeah, there we go. I also have to warn you that there's a lot of concepts in this chapter that I don't even understand. Okay, because I'm not perfect. So, but I can tell you line integrals, and this is a key foundational moment here. Line integrals. I wonder if they have a picture. Yeah, what's up?
I have a question.
Yes.
Oh.
No, because we have 2 missing people.
Okay.
I would like to do them when everyone's here.
Okay.
Yeah. So maybe next Tuesday or something.
All right.
Is that cool?
Yeah, that's cool.
Okay, cool.
Yeah.
So line integrals. This is an okay picture. This is a way better picture. Okay. So integration is area under the curve, right? So now our curve is in 3D space. I want area under the curve. There it is. There's your line integral. I can't say it's area necessarily because it's area underneath the curve. And what would you call that, an area? So it's kind of a weird concept, but it does work. And we're going to use it to find distances and all kind of little formula thingies as we keep going, okay? So line integrals, very, very important thing there. Whenever you see a DS, you don't do it, okay? So that's a bad formula. rather, we're going to use it just whenever they say ds, you're just going to say, oh, yeah, well, we converted. And they're already converting this v for you right here. So, like, the real formula, if you want it, is integral of f times the square root of x prime squared, y prime squared, z prime squared, dt, I guess. I don't know. There you go. It's a very rough formula. I don't like this formula, but you get the picture. We're going to have little derivatives. We're going to plug things in. It'll be fine. Only one integral right now. Only one integral right now. Yeah, he just randomly shows up. So, it says, do it. DS. And you're like, So in a way, I'm going to say that the ds converts it to this magnitude VDT thing, okay? So this used to be a ds, and now we're converting it to this magnitude of VDT kind of thing, okay? So we're doing good things. We just need to figure out what they're wanting. Okay. First off, it says integral of x plus y. Do we have an x?
Yes.
Oh, look at that. Do we have a y? Oh, look at that. And then I'm going to say times this magnitude of v. Again, v is just first derivative. So I want to take my first derivatives and square them. What's my first derivative of this guy? And then you square it. First derivative of this one, square it, and then derivative of this guy? Sweet. dt. So again, the ds is all this stuff. That's ds. And then this is our function that we just plugged in, which was like right here. Okay? Now, I need to find a t value where it's starting and stopping. And you notice that they give us these points here, and I'm totally ignoring the last one because obviously z equals 0 the whole time. If z equals 0 the whole time, it's meaningless for what we're looking for. What? Go ahead.
Oh, I was going to say, wouldn't our limits be from 0 to 9?
Well, maybe. But you're definitely getting the right zone. Like, let's look at x just alone for a second, right? So I'm saying that x is equal to 0, and I'm saying that x is equal to 9. But I'm saying that x is equal to 3t. What I want is the t values that make that thing work. So if you want me to go very crudely, 0 equals 3t. What is t? Okay. 9 is equal to 3t. 0 to 3. And you can confirm with the y's by plugging in the 9 and the 9 and stuff, and you'll see the same kind of idea. It's kind of similar to that Jacobian stuff we were doing, but like far easier. You're just plugging in some numbers. Now, I smell something very good. Y'all not smell that? It smells like roasted bread? No. You do?
Kind of.
It smells like pizza? It will be pizza here soon. Meaty. Okay. Sorry for the folks at home, you don't smell that. But it actually smells really good. Or maybe I'm just really hungry. Let's put this all together. Chad, you're writing way too big. Nah, I'm fine. So, looking right here, what would this function end up being right here? 9. Just a 9. Huh. And then we got square root of, yeah. Okay. Square root of 18, exactly. So we got 9 square root of 18 integral dt. Very good. 27 square root of 18. You got it. You just multiply by the 3. So let's flash the answer because I did not do it. I did not expect us to get this far. 81 over square root 2. What? What?
Oh, yeah, because you can factor out a 9 from the 8.
You know what? So you're saying that this is 9 times 2.
Yes.
You're saying that I can say that's a 3. and then you're saying that this is this. Okay. I really thought I had messed up, but like I was like, this is a pretty simple problem. Okay, good, good, good. And we wrote super huge this time. Does it feel good to do that?
Yeah. But now I'm nervous, Chad.
So not hard though, not hard. Line integrals are easy. I think it's when we start using them inside of other things, they start to get more complicated. Going forward, we have Green's theorem, Stokes' theorem, divergence theorem, just lots of little things that make it more. And some of them are easy and some are not. So, is this okay though? Overall, not too bad. We're just basically using a formula. And DS is scary, so we always just convert it and be happy and be done. All right, before I go diving deep over here, I feel like I just want to find this magnitude of V thing. What's my derivative in terms of x? Derivative of x. 2t all squared. And for my y? Perfect. And all that squared. Whop. If we don't have a z at all, then just leave it alone. It'll be fine. I want to make this a little bit better. 4t squared plus... Yeah. I know we can simplify that. Oh, I just said the S word. I'm so sorry. But it'll be helpful for integration here later. So what can I factor out? Yes, yes, indeed. You can take a t squared out, leaving this behind. If I had to integrate just that guy, not too bad now, huh? Because you sub stuff. That's not what we're doing, but I'm saying at least it's down a good road. Okay, so I like this guy. And then all I'm going to do is tack in these other ones. So, well, oh, one last one. Oh, yeah, with the t's. They already gave it to us. That's nice. Okay, so my t's are easy. So x squared, I already have an x. So that's t to the fourth. In the bottom, when I plug in a 3, how many t's do I get in the bottom? Again. Well, that's strange because I just said, oh, if I had to integrate this all by itself, it would be really nice. I did not know that would happen. I just figured it would be something like that. Yeah. du is 18t dt. What? Did I hear groaning?
No.
Oh.
I reached in my pocket so I can get a calculator.
Oh. Sure. The t's cancel. The 1/18th can come to the front. That's u to the 1/2. Integrating. 2/3 u to the 3/2 from 1 to 2. Half of the 18 is going to be a 9. 9 times 3 is 27. Plugging in the 2. Say that again? 76 to the 3/2 minus, I plug in the 1. I got this one. It's a 13. Did I do it right? Okay, good. Thank you. And then we have to no. We don't have to do anything. 80 and 13? Where'd the 80 come from? Square root of 10. Yeah, probably is a good answer. Just probably. Okay, 76. So, do we have a 4 in there? No! Okay, hold on. Let's do it. So, 4 plus 9 times 4. Oh. blame it on me. It's okay. Chad, your handwriting was terrible. So there's a 4 in there, and then I can cube it as it comes out. So it'd be a 2 cubed is an 8, square root of 10. And then this guy I'm just gonna leave alone. Was it 8 or 8e? So did I have another 10 in there I didn't think of?
Well, is it square root of 10?
Oh, and it's cubed. So this is technically 10 square root of 10, all that stuff.
So you multiply by 10.
Yeah. It's basically, for the folks at home, it's this, and this turns into 10 square root of 10. 10's on the outside, make an 80 there. Yeah. Okay. We did it! Woo! You can see, not hard though, right? Not hard. Yet. I really think Jacobians are pretty much the pinnacle there, but Stokes' theorem is right behind it, man. You'll be so stoked once you get there. Okay. We have 8 minutes, and I need to get pizza. So, can we just call it here? Is that okay? You don't want to do too many new things. So I'm done. Stop recording. Bye.